The next result we want to prove is the Galois correspondence for covering maps. So this correspondence will come in the next lecture. But in this lecture we will discuss some preliminary things. So throughout this discussion, X will denote a connected and locally path connected topological space. So definition: a path connected space X is called simply connected if the fundamental group is trivial. By a pointed topological space, we shall mean a pair X and X naught, where X naught in X is a point. A map of pointed topological spaces is a map F X X naught to Y Y naught, where F is from X to Y and F of X naught is equal to Y naught. So theorem: let P from X tilde X naught tilde to X X naught be a simply connected cover let F from Y Y naught to X X naught be a say connected cover then there is a unique lift F such that we have a commutative diagram this F. So the proof: use that the fundamental group of x tilde is trivial, and apply the lifting theorem. So as a corollary, we get two connected and simply connected covers are homeomorphic. So proof that Pi for I equal to 1 and 2 xi P2 connected and simply connected covers then by the lifting theorems that we just saw, we have lifts there is F, there is G, such that so we have lifts F and G, but this implies that G compose F of x1 tilde is equal to x1 tilde, and by uniqueness of lift we get G compose F is equal to identity. Similarly, F compose G is equal to identity. So in view of the above, so this completes the proof of the corollary. Corollary, it follows that if X is connected and simply connected and locally path connected, topological space then connected and simply connected cover, if it exists, is unique up to homeomorphism. Such a cover is called a universal cover, and the term universal is because theorem 1 shows that it has a universal property. So next we'll consider deck transformations. So let P from x tilde x naught tilde to x naught be a universal cover. So we define automorphisms of P to be the set of maps F from x tilde to x tilde such that F is a homeomorphism and P compose F is equal to P. So in other words, F is a homeomorphism and it's inside this commutative diagram. Clearly, odd P is a group under composition of maps. There is an action so let's call the map A from odd P cross x tilde to x tilde, which ends F comma x tilde to F of x tilde. So before we analyze this action, let's recall some terminology related to group actions. We call the following terminology. Let G be a group acting on a set S. We say that the action is transitive if there is only one orbit. That is, for some S and so for all S, the orbit of S, that is G dot S for G in G, is equal to S. So this is a transitive action. So we say the action is free if for all S in S, the stabilizer S is trivial. So note that in particular, if the action is transitive and free, Then the map G to S defined by G goes to G dot S naught, where S naught is any element of S, is the bijection. So, having recalled these definitions, let us come back to the situation of odd P acting on X tilde. So it is easily checked that odd P takes the fiber P inverse X to itself. And therefore, it defines an action. Therefore, there's the action, induces an action on the fiber P inverse X. And the proposition is the action of odd P on P inverse X is transitive and free. So the proof, let x1 tilde and x2 tilde be in the fiber over X by the lifting theorem. There is F in odd P which makes the following diagram commute. Which implies that f of x1 tilde is equal to x2 tilde. So this implies odd P acts transitively on P inverse X. Similarly, again using the lifting theorem, if f of x tilde is equal to x tilde, then by uniqueness, of the lift, we get that f is equal to identity. So this implies action is free. So in the same way, okay, so we have a similar proposition. So but before that, so we have the same notation. P is a universal cover let V contain X be a path connected open set which is evenly covered. Then P inverse V breaks up into a disjoint union indexed over T in P inverse X. So it breaks up into a disjoint union of sheets. Each sheet contains a unique point which lies above X. That point we call T, and we index these sheets by UT. So since each u sub t is homomorphic to v, it follows that u sub t is path connected. And so is exactly, and so these UTs are exactly, so thus the UTs are exactly the path components of P inverse V. So proposition with notation as above. Or P acts freely transitively on the path components of P inverse V. So proof. So it is clear that odd P maps P inverse V to itself. P inverse V to P inverse V. So as before, let T1, T2 be 2 points in the fiber over X. Then there is a unique F such that F of T1 is equal to T2. So then it is clear, since the UTs are path connected, that F of UT1 is contained in F UT2. Moreover, since F restricted to UT1 is equal to P restricted to UT1 and then P restricted to UT2 inverse. So this implies that F from UT1 to UT2 is a homomorphism. So thus F permutes the path components of P inverse V. And by uniqueness of lift, it follows the action is free. So this is very similar, and we leave the details to the reader. So using this, let us prove the following proposition. So we give odd P the discrete topology, then there is a commutative diagram in which all arrows are continuous. So proof. It is clear that the diagram is commutative. We only need to check that A is continuous. So let us do that. So let B be the collection of open sets U in X tilde such that U is path connected and P of U, which is open inside X, since P is a covering map and so it's open. That is something which we had seen before. So we want P of U to be evenly covered. Is an evenly covered open subset. It is easy to check that P is a basis for the topology on X tilde. Thus, it suffices to show that A inverse U is open for all U in P. So let's show this. So suppose A of f comma x tilde is in U. So that is f of x tilde is in U. Let x be p of x tilde and let v be equal to p of u. So by assumption, by the definition of u being in B, V is evenly covered. And so P inverse V breaks up as a disjoint union T in P inverse X qt. So in particular, we have the sheets u x tilde and u of x tilde over V. So since F permutes the path components of P inverse V, we get that f of u x tilde is exactly equal to u of f of x tilde. So u of x tilde is exactly equal to u, because u of f of x tilde is the unique sheet which contains f of x tilde, and that is u. Thus we get that a of f cross u x tilde is contained in u. This implies that f cross u x tilde is contained inside A inverse U. Thus, A is continuous. So, for simplicity of notation, let us denote G equal to odd P. So by x mod G, we mean the following. Put an equivalence relation on x by defining G dot x is equivalent to x. Then the equivalence classes are precisely G orbits. So let x mod G be the set of equivalence classes or G orbits and with the quotient topology. So we have maps. So in this discussion, we take, okay, so this should have been x tilde. So we have maps x tilde to xp, and then we have the quotient map. So if x tilde is in x tilde, then p of g dot x tilde is equal to p of x tilde, which means the entire equivalence class maps to the same point. Thus, by the universal property, of the quotient map, we get a unique continuous map Q from x tilde mod g to x. So we can use pi, and there is this unique map Q, which makes this diagram commute. Since and Q is continuous, since G acts freely and transitively, on P inverse X, it easily follows that Q is a bijection. So we will now show that Q is an open map which will prove that Q is a homeomorphism. So theorem, Q is a homeomorphism. So proof, let U contained in x tilde mod G be an open set, then pi inverse U is open in x tilde, by the definition of quotient topology. Since P is a covering map, it is open, and so P of pi inverse U is open in X, but P of pi inverse U is equal to Q compose pi of pi inverse U, which is equal to Q of U. Since pi is surjective, we have pi of pi inverse U is equal to U. So this implies that Q of U is open. So as a corollary, we get that Q identifies the maps pi and P. So in other words, we can recover, so x tilde to P, the space X and P are recovered as x tilde to x tilde mod G. This pi, sorry. So motivated, by the above discussion. Let us define. Let G be a group acting on X such that the action is free that is for all X in X, we have that the stabilizer of X is the identity. And 2, for every X in X, there is an open set U containing X such that G dot U intersected with U is empty if G is not equal to identity. So if these two conditions are satisfied, then we say that the action of G on X is a covering space action. So from what we saw above, earlier, if P from X tilde to X is connected and simply connected cover, then firstly odd P acts on X tilde by a covering space action, and secondly the map P is recovered as the quotient map X tilde to X tilde mod odd P. So a simple example to keep in mind is the map P from R to S1 given by P of X is equal to e to the power 2 pi I X. So there is a natural map from the integers to odd P given by an integer n. It goes to the map translation by n. So this map is a bijection. So it is clear that it is an inclusion and to prove that it is surjective, we can see it as follows. Is seen as follows. So given f in odd p, so f of 0 is some integer n, then t minus n compose f is in odd p, and t minus n compose f of 0 is equal to 0. So by uniqueness of lift, we get f is equal to t minus n. So anyway, analogous to the situation of the map P from x tilde to x being recovered as the quotient map x tilde to x tilde mod odd P, we have the following proposition. Well, before proving that, let G act on X, and suppose the action is a covering space action. Let X mod G tilde, X mod G denote the space of G orbits with the quotient map by X2 X mod G. Then pi is a covering map. So proof. So let X in X. So then there is a neighborhood U containing X such that G dot U intersection U is empty if G is not equal to identity. So we claim that pi of U is an evenly covered open neighborhood of pi of X in X mod G. So first note that pi inverse of pi of U is exactly equal to the union of G in G, G dot U. But since, because of the condition G dot U intersection U is empty if G is not equal to identity, is exactly equal to the disjoint union G in G, G dot U. Thus, pi of U is an open subset by the definition of quotient topology. So in fact, pi inverse of pi of V for any set v is just g dot v, and if v is open, then this is open, so this implies pi is an open map. So we claim that pi restricted to u from u to pi of u is a homeomorphism. So we have already proved that this is an open map. So this map is open, continuous, and it is clearly bijective. So it is bijective because it cannot happen that if x and y are in u and pi of x is equal to pi of y, so this implies that there exists g in G such that g dot x is equal to y. So this would imply that g dot u intersected u is non-empty, which would imply that g is equal to identity. So which implies x equal to y. Thus, pi restricted to u is a homeomorphism. And finally, G sits in a commutative diagram which implies that pi restricted to u is equal to G compose pi restricted to G dot u, which implies that pi restricted to G dot u is equal to G inverse compose pi restricted to u, which implies that pi restricted to G dot u is a homeomorphism. So this implies that pi from x to x mod g is a covering map. So now we can prove the following theorem. Let x tilde be a connected locally path connected and simply connected space. Let G act on x tilde and assume the action is a covering space action. Let x be equal to x tilde mod g and let pi from x tilde to x denote the quotient map. Then there is an isomorphism G to odd pi. So proof. First, it is clear that any G in G sits in a triangle x tilde to x tilde x x. So this shows that there is a map G to odd pi. So clearly, this is an inclusion. So we need to show that this is surjective. So we fix an x tilde inside x tilde and let f be any element of odd pi. Then f of x tilde belongs to pi inverse of pi of x tilde, and so f of x tilde. So this is a G orbit. You have to keep that in mind, and therefore you will get f of x tilde is equal to G dot x tilde for some G. So since G inverse compose f of x tilde is equal to x tilde, by the uniqueness of lift, we get that G inverse compose f is equal to identity. So here we have used the fact that so we have x tilde comma x tilde. This is pi. So by the previous proposition, pi is a covering map, and x tilde is a universal cover because x tilde by assumption is simply connected. Okay, so this is and we have this lift G inverse compose f. So since we have already proved that pi is a covering map and x tilde by assumption is simply connected, so we can use the earlier theory that we have developed. So this completes the proof. So this implies this natural map from G to odd pi is an isomorphism. So to conclude, we can sum the discussion as follows. So x tilde is a connected, locally path connected and simply connected space G acts on x tilde by a covering space action. Then first the map x tilde to x tilde mod G is a covering map, and second mod pi is isomorphic to G. We get back G. So we will end here.